This project was inspired by the Hackaday Prize Energy Harvesting Challenge. I wanted to create a device that could harvest energy from the heat of a hot cup and set off an alarm once the perfect temperature to drink was reached. The two main constraints I set on myself was that it had to work with a ceramic mug and that nothing needed to go into the drink itself. This device uses a thermoelectric generator to generate electricity. My talented friend Jason shaped a copper slab for me, as copper is great for transferring heat. A computer heatsink with thermal paste is mounted above the generator to keep cool side cool. The larger the temperature differential across the generator, the more electricity is generated. The voltage shown on the multimeter relates to the surface temperature read by the device above the copper, a thermopile. A thermopile measures temperature at a distance based on infrared radiation. A thermopile output also depends on ambient temperature, so a thermistor is used to help negate the offset caused by changes in ambient temperature. The circuit isn't very well calibrated, so the output voltage varies more than it should. A breeze or sudden change in airflow can affect the reading. At high temperatures, the sensor is very unstable for me due to the large amount of evaporating water creating varying air currents. The device is entirely run by analog circuitry. No microcontroller has been used, so as to use the least amount of energy possible. The LED will turn on if the voltage displayed falls below about 0.45 volts. I also explored using a fan to cool the drink down, which also serves to cool down the heatsink. I took some temperature readings to figure out how long it took a cup of hot water to cool down to 60 degrees Celsius on its own, next to the copper heatsink, and with a fan running while next to the copper heatsink. Just having the cup next to the copper decreased the cooling time by a minute. Having the fan on decreased the time by several minutes. As the temperature drops, the output of the sensor begins to stabilize more. Occasionally, airflow can cause false negatives, with the LED turning on briefly before the sensor stabilizes. My voltage comparator circuit uses hysteresis so that the LED turns on at a level such as 0.455 volts and won't turn off until it goes above 0.46 volts. I need to increase this spread to decrease how much the LED turns on and off. As seen here, only a tiny amount of energy was generated, hundreds of times less than the monitoring circuitry uses. Not every experiment has favorable results. To determine the amount of energy generated, I recorded the amount of current generated at each stage for standard cooling and cooling with the fan. With the fan, the current generated rose very fast and leveled off around 40 microamps. Just after the cup was removed, however, the energy generated fell off quickly. These results show that even though the copper stays hot for a while after use, it is not hot enough to charge the battery. A big part of this is that without the fan, the temperature differential of the TEG falls as the heat continues to flow. Without the fan, the energy generated peaked much lower and gradually fell, far before the cup was removed. The reason for this mentioned above was the fact that the heatsink could not exchange the heat fast enough without the fan, causing the temperature differential to fall. As the energy used by a fan far outweighs the energy generated, with this fan running, the energy harvesting extends the life of the battery by about 0.023%. Without the fan, the energy harvester extends the life of the battery by about 0.15%. Assuming the full milliamp rating of the battery can be used, the device without the fan can run 1,849 times. 3 of those times are thanks to the generated energy. The device is also able to generate enough electricity for one full use after 577 uses. The generating and charging circuit employs the use of an energy harvesting chip. The chip operates by pulsing energy from the thermoelectric generator through the transformer to begin collecting energy. The output of the energy harvesting chip goes into the battery charging monitor in the bottom left to help charge a lithium-ion battery. This charging module restricts the current supplied to the battery so that the generated source isn't overloaded. Without this, the source would overload, dropping the voltage significantly, so that it wouldn't be able to charge the battery. It also ensures the battery isn't overcharged. The resistor network on the left is for linearizing the output of the thermistor, which can help offset the effect of ambient temperature so the thermopile can accurately measure surface temperature. A thermopile requires no energy to output a voltage, but it only outputs a tiny voltage. The output is amplified 100 times and goes into a comparator. Once the value reaches the reference voltage, the LED conducts. The voltage shown here at the potentiometer is a bit outdated, it is actually a bit higher.